Hello everyone. Today we will see subspaces in the series of lectures on linear algebra. So this is in the module 1 and then this is the third lecture in the series. So what is our agenda for today? Today we'll see what is a subspace and we'll see some of the examples and we'll see an equivalence definition of subspace, and also we'll define something called coset, and we'll see a linear combination. What do you mean by linear combination? And coming out of it, we'll see what is a span, and we'll look into the special subspaces, something called column spaces and row spaces and etc. So that's our plan for today. So let's see what is a subspace. uh, Whenever a vector space is given, suppose V is a vector space, then consider a set W which is completely contained in V. Then I would like to call this W as a subspace if W itself is a vector space under the same operation which has been on V, which means I say W is contained in V is a subspace if W is a vector space with respect to the same under the same addition and scalar multiplication which is defined on V over the field same F, which is where in which V is a vector space over F, which means suppose if I say V is a vector space under addition and then scalar multiplication over F, then W is called as a subspace if W itself is called is a vector space over the same addition and same scalar multiplication and over the same F. So this is a definition of a subspace. Some of the examples, suppose I know that R2 is a vector space, R cross R is a vector space. Now I also know that any line passing through origin is a vector space. So say for example y equal to x line, so this is a vector space. So if I see this W is equal to set of all x comma y such that x equal to y and x comma y belongs to R, then this is a subspace of R2. So W is a subspace of R2. In fact, because W itself is a subspace in which is completely contained in R2. So this is my first example. You can see any line passing through origin is a vector space which is completely contained in, of course it has to pass through origin, and any line passing through origin is completely contained in R2, and each line passing through origin is a vector space. Therefore any line passing through origin is a subspace corresponding subspace of the R2. More generally, you can say any plane or any plane passing through origin is a subspace of one dimension more than that, or the vector space means what I mean by that is, suppose if Rn is present, then any line a1x plus a2 a1x1 plus a2 x1 x2 plus and so on up to an xn. Suppose this is equal to 0, then set of all points of this kind is also a subspace. So this kind is also a subspace of Rn. We can prove that in that manner. Anyway, I will technically define what is this in the future examples, not now. What else I know? I particularly know one of the specific example whichever we have done here. Say for example real valued functions which is continuous real valued functions, which is a vector space we have proved, and we also know that this is contained in set of all functions. So if you see the set of all functions, and that if you see that as a vector space, and if this is as a W which is completely contained in V, since this itself is a vector space, therefore W is a subspace of V. In fact, the third example would be something like, if you consider all the polynomial of degree less than or equal to n, which is completely contained in the C of R, and which is completely contained in set of all functions. Therefore, Pn of x is a subset of C of R, and by itself is a vector space. Therefore, this is a vector space of C of R, and this is a vector subspace of C of R, and this is a subspace of this set of all functions S, and therefore Pn of S is also a subspace of S itself. Okay, so likewise I can generate many examples, but before that I would like to quote one theorem which is giving you an equivalence definition to verify the given set is a vector space or not, or sorry, given set is a subspace or not. So the theorem, let's discuss this. Let W is a subset of V. Let's take a non-empty subset of V. Then W is V is a vector space over any field F. So VW is a subspace if and only if for every alpha in F and for every u comma v in W, alpha times of u plus v belongs to W. So this is the equivalence theorem, and that gives the characterization for W to be a subspace of a given vector space. Proof is very simple. It is much easy to identify. Let's say suppose W is a subspace. The forward implication is actually trivial. I can just explain it by words. Why? Because if this is a subspace, then by itself it's a vector space. So you take any two vectors and then a scalar, a linear combination of that will be definitely belongs to W. That is clear for that is clear from the definition of the binary operation, means the plus is binary operator. Therefore, the forward implication is trivial. What about the reverse implication? Let's say suppose W is a non-empty set is being given. So let's say W is a non-empty subset of V, and so this implies there always exists one U, right? So there exists one U in W. That's what it means. Now let's see, suppose whether closure property is satisfied or not. The first property is closure property, which is checking that whether plus is binary or not. Clearly binary, because that's what the definition, that's what the hypothesis given here. For every alpha in F and for every u comma v in F, we know that it is alpha times of u plus v W belongs to W. So the binary property is already satisfied. The second thing which I have to check is commutative property and other property. But if you clearly watch, then the commutative property and other some of the properties no need to be verified. Why? Because look at the definition of vector space over here, which is from the previous lecture. These properties, whatever I am quoting here, this commutative property is not depending on any particular set of V or any particular subset of V. It's called a parent property, which means doesn't matter whatever the W, these properties are going to be satisfied, because either you take u and v belongs to W or V, this property is anyway going to satisfied, because u and v will be always there in the vector space itself. Okay, so similarly associative property also I don't have to verify, and similarly I don't have to verify this 1 dot u equal to u as well. I don't have to verify this particular associative property with scalars, and I don't have to verify this property as well. This is a scalar distribution. It's a distribution of scalar among the vector addition. It's also known to be verified, and similarly the distribution of vector with the scalar also no need to be verified. So these properties are all actually called as parent properties. So we don't need to verify any parent properties. So the left to verify is only the third property and the fourth property, which is I have to check that whether 0 is in the set or not. Means is there any identity exist, or as well as for any given u in W I need a negative of that so that I will get the identity, which means inverse exists or not. That's what I have to check. Let's go to that. So I wanted to check the existence of 0. So how do I check the existence of 0? Let's say suppose u belongs to W, which I know, this is clear. So u is already there in the W because W is a non-empty set. Now since alpha times of u plus v will be always in W for any u and v in W, let's say v is also u, therefore alpha times of u plus u must also belongs to W. In particular, what I can say is, in particular, if alpha equal to minus 1, then minus 1 into u plus u must also belongs to W, which means minus 1 into u is nothing but minus u. That's what we have proved in the last lecture. For any vector space, then that is true. So therefore this is minus u plus u, which is W, but minus u is the inverse of u, because u belongs to vector space V, and then we know that who is the inverse of u. So which means minus u plus u is 0 from the vector space definition, and that must belongs to W. That's what we have proved. What we have proved? So we have proved that 0 belongs to W, and if this 0 is a identity for V, then this 0 must be also an identity for W. That is clear, correct? I just wanted to verify that whether 0 is inside the W or not. That is, must be inside the W because of the definition, because of the hypothesis. Now the left to verify is the existence of the inverse for any given element u in W. So let's verify that. So the third one is, let u belongs to W. Now I have to verify that whether minus u belongs to W or not. That's it. How do I verify that? That's also pretty easy to verify. I know that u belongs to W, therefore what I can do is minus 1 times of u plus 0 also belongs to W. That's clear, because you see you see alpha can be taken as minus 1, and then v can be taken as a 0 vector. Therefore minus 1 times of u plus v 0 is also belongs to W, and that gives me minus 1 times of u belongs to W, but minus 1 times of u is nothing but minus u itself, so minus u must also belongs to W. So that's what we know. How did we prove that? It's pretty simple to realize it. U belongs to W, which is completely contained in V, which means there exists minus U. That is for clear. Our claim is whether that minus U belongs to W or not. I have proved that minus U must belongs to W using the hypothesis, because I have alpha times of U plus V always belongs to W for any U comma V in W. That's true. So this proves that W is a subspace. W is a subspace. That's what we have proved. Okay, so this is a very important theorem which we have proved here right now. So what we have proved, if W is a non-empty set which is a subset of a vector space V, then W will be a subspace of V if and only if for every alpha in F, for every u comma V in W, alpha times of u plus V must belongs to W. Okay, fine. Using this we can prove many things. We can prove, you can in fact verify whether the given set is subspace or not. This is much easier to verify instead of verifying all the vector spaces. Okay, some of the examples which I can right now supply. Example number 3. Let's consider a set of all matrices of order n. This is a set of all matrices of order n. Now look into the set W1 is equal to set of all symmetric matrices, which means set of all matrices A in M such that A and A transpose are same. Okay, A and A transpose are same. Now what we know is set of all matrices over of order n, either over R or over C, it's going to be a vector space. So I'm going to write it as over R right now. You can also write it as C, that doesn't matter. Okay, so that's going to be anyway vector space. So Mn is a set of all matrices of order n over R. It is a vector space under usual addition and scalar multiplication. Now look into this set W1. This is clearly a subset of Mn. Now I can say that this is a vector space by itself. In other words, this is a subspace of Mn. So how do I prove it? Proof is much more simple. I just have to verify that whether alpha times of A plus B belongs to W1 or not, right? whenever A and B are belongs to W. So let's take A, B belongs to W1, and then alpha belongs to R or C. So what will happen to the A alpha times of A plus B? Now I know that A equal to A transpose. I just have to verify that alpha A plus A B whole transpose is same as that of alpha A plus B itself. Okay, how do I verify that? It is very simple. I can write I can directly write, no, I can write alpha times of this is A transpose plus B transpose, because A belongs to W1, and therefore this is equal to, I know that alpha times of A transpose is alpha A times of transpose, alpha A transpose, and this is B transpose. And we already know that A plus B transpose is equal to A transpose plus B transpose, and therefore this is alpha A plus B whole transpose, which shows that alpha A plus B must be equal to alpha A plus B whole transpose, which means this is symmetric matrix, which evidently says that W1 is a subspace. So this implies W1 is a subspace. So that's the advantage of proving that theorem. It helps us to verify that whether given set is a subspace or not very simply, very easily. Okay, first of all, I have to verify the non-emptiness. To verify the non-emptiness, is most likely most of the authors will verify that whether 0 belongs to W or not, right? Which means question was whether zero matrices is a symmetric matrix or not. That's what we have, right? So W1 is a subspace because of this 1, and the 0 matrix also belongs to W1. Therefore non-emptiness is been captured here, and then the 1 is telling you the hypothesis which you were supposed to prove as subspaces. Okay, so the next example, the fourth example would be, maybe I can take many other examples. I can consider the same Mn itself, and let's consider W2 is equal to its set of all diagonal matrices. See all the matrices A such that Aij is equal to 0 for all I not equal to j, correct? So these are all called as diagonal matrices. You can verify that W is again a subspace of Mn. Why? Because we just have to verify that whether sum of two matrices is diagonal or not, and alpha times of A plus B is a diagonal matrices or not, and whether I have the identity matrix inside it, whether I have the zero matrix inside the W2 or not. Clearly everything is true. Therefore W2, which is set of all diagonal matrices, this is actually set of all diagonal matrices. Set of all diagonal matrices is a subspace. Diagonal matrices is a subspace of Mn. That's clear. Why don't you verify one more thing as well? So W3 you can consider as set of all matrices A such that trace of A is equal to 0. It's a special subspace. Trace of A equal to 0. How about this? Is it a subspace? Yes. Why? Because roughly I am writing. So look into the trace of A equal to 0. The 0 matrix always 0 is 0. Therefore 0 matrix is always in the W3. That's clear. Therefore what about I have to check only alpha times of A plus B, that much only. How am I going to verify that whether this trace is 0 or not? Okay, so this is very simple. I just have to verify the trace of alpha times of A plus B, and that is equal to alpha times of trace of A plus trace of B. This and all is very simple to prove. One can actually just prove it using your matrices technique, just element wise addition. And this is actually trace of A is always 0 because A and B are from W3, and then this is again 0. Therefore alpha times of 0 plus 0 is actually equal to 0, which means trace of alpha A plus B must be 0 for any A and B belongs to W3. So that proves that if you collect all the matrices A whose trace is equal to 0, then that is also a subspace. You can ask many questions on set of all whether invertible matrices, whether they are forming a vector space or not, or set of all positive definite matrices, whether they are forming a subspace or not, set of all non-negative matrices, whether they are forming a subspace or not, and so on. Yeah, non-negative matrices reminds me one thing. Why don't you check that whether non-negative matrices forms a subspace or not? That's very clear, no? Suppose I say W5 equal to set of all non-negative matrices. Non-negative matrices. Is it a subspace? Obviously, this is not a subspace because you can verify it with a bigger example, but I will give one special example. Let's say, suppose I have a 1 1 1 0 0 1. It's an identity matrix, and then let's say minus 2 0 0 0 1. Doesn't matter. So this is equal to minus 1 0 0 0, right? Definitely, this is not a non-zero matrix. This is not a non-negative matrix. Therefore, binary operation is not being satisfied, which means if I wanted to clearly write plus minus 2, then plus minus 1, that's also fine. Anything is fine for me. Therefore, set of all non-negative matrices is not a subspace of Mn. Okay. Similarly, you can verify other matrices as well, whether set of all singular matrices forms a subspace or not. All these things and all we can do. Okay. We'll see special thing from matrices itself. What is the number? 5, right? So let's say, suppose given a matrix given a matrix A, in fact given any transformation, linear transformation, in fact for any linear transformation which I have not introduced yet. So once I introduce this, then this sentence will make sense for you. But given a matrix A, then we can define two different sets called range of A and then kernel of A. So there are two different sets which are special sets in matrix theory. If this matrix order is m by n, then the range of A has been defined as set of all A into X such that X belongs to Rn. X belongs to Rn. Now this is a subset of Rm. This is a subset of Rm. Now kernel of A is defined as set of all X in Rn such that Ax equal to 0. Correct? So this is a subset of Rn now. Now these two are very special sets, very special subsets which is related to a matrix A. Once we go to linear transformation, I'll explain more about what is range of A and kernel of A. As of now, we just have to remember that these two are very special subsets. Now these subsets, if you see, then this will also be a subspace of Rm and Rn respectively. You can verify it without any problem. In fact, given any linear transformation, then you can define this range of A and kernel of A, and correspondingly it will become subspaces of the respective vector spaces in which it is subset. You can verify it very easily. Okay. So let's see one more theorem for the purpose. Let W1 and W2 be two subspaces of V. Then what about question number 1? What about W1 intersection W2? And then what about W1 union W2? You can also ask for W1 difference W2 and all these things and all. Whether the set operations on two subsets of V is following subspace or not. That question can be asked. Okay. So this is a subspace for sure. I can prove it. We'll prove it. Whether this is a subspace or not is a question mark. If that is not a subspace, then what condition will make this W union W2 is a subspace is a question mark that we will answer separately. Now let's see. Suppose so I'm not going to prove anything on this. I'm going to prove on this. Okay. So the proof. Let's say W1 intersection W2. Definitely this is a subset of W1 as well as and W2, and therefore it is a subset of V, and therefore W1 intersection W2 is a subset of V. That's for clear. Fine. Now its a non-emptiness has to be proved. That is can be proved very easily. That just verifying that whether 0 belongs to W1 intersection W2 or not. I am saying that is true. Why? Because 0 belongs to W1 because this is itself is a subspace, as well as 0 belongs to W2 because W2 is also a subspace. Therefore 0 belongs to W1 intersection W2. So that actually shows that W1 intersection W2 is non-empty. That's clear. Now what we have to do, we have to verify that alpha times of u plus v belongs to W1 intersection W2 or not for any u and v belongs to W1 intersection W2. So let's say, suppose let alpha belongs to the field F, and then u comma v belongs to W1 intersection W2. Now proof is very clear. Why? U belongs to W1 intersection W2, which means that this implies u comma v belongs to W1 and W2, correct? I'll write it in short notation. Now this means what? What about alpha u plus v? So alpha u plus v, since u and v belongs to W1 and alpha belongs to W1, so alpha u plus v must belongs to W1. Because of this, u and v belongs to W1 and alpha, and W1 is a subspace. Similarly, u and v also belongs to W2 and alpha belongs to F. Therefore alpha times of u plus v must also belongs to W2 because W is a subspace. So therefore it must be there in the intersection. So alpha u plus v must be there in the W1 intersection W2. So that makes that W1 intersection W2 is a subspace using the previous theorem. Okay, so if W1 and W2 be two subspaces of V, then W1 intersection W2 is always a subspace. That is for clear. So now let's ask the question of when the W1 union W2 be a subspace. That's my question. When this will happen. Let me give it as a theorem itself. Suppose W1 and W2b are subspaces, then W1 union W2 is a subspace if and only if either W1 is contained in W2 or W2 is contained in W1, which means one is contained in the other. Proof. What is the proof? One way is trivial. Which way is trivial? The counterpart is trivial. Why? If W1 is contained in W or the other cases, then in the W1 union W2 is going to be one of them. And one of them is already, means both of them are already subspaces. Therefore, W1 union W2 is a subspace. So that is trivial. I don't have to worry much about it. Now, what is the forward implication? To prove the forward implication, I have to assume that W1 union W2 is a subspace. So that is clear. So we know this. So let W1 union W2 be a subspace. Now question was what about W1 contained in W2, whether that is true or this is true. Let's say W1 suppose is not contained in W2, which means there exists one U in W1 such that this U is not in W2, correct? Now what we have to prove is if this is not happening, then this should happen. That's it, right? Correct? Which means W2 should be contained in W1, correct? That's what we have to prove. Think why. Usually it's not much obvious, but you can think it. It's very simple to think. Which means I have to say, suppose I take one element V belongs to W2, then I have to prove that V is also in W1. That's what I have to prove. Okay, how do I prove that? Now let's say, now what about U plus V? U plus V must be belongs to W1 union W2. Why? Because U belongs to W1 and V belongs to W2. Therefore, U and V must belongs to W1 union W2. And addition is binary. Therefore, U plus V must belongs to W1 union W2. Now since W1 and W2 both are vector spaces, then what I can do is I can look for the inverse of V. Means inverse of V is there, so U plus V minus V, sorry, minus V, uh, U plus V belongs to W1 union W2, which says that whether U plus V maybe belongs to W1 or U plus V belongs to W2. So either one of them can happen or both can happen. Now suppose if this happens, what will happen? Suppose U plus V belongs to W2, then what I can do, I can add with the inverse of V, and that also must belongs to W2 because W2 is a subspace. But addition of this is nothing but U, so U belongs to W2, which is a contradiction to our assumption that U is not belonging to W2 in the previous slide. So that's what is a contradiction to this, correct? So therefore this cannot happen. So therefore this implies U plus V must belongs to W1 only. When this can happen, then what we can do, I can add it with the inverse of minus U, the inverse of U, so that is minus U plus U plus V, that belongs to W1 because U belongs to W1, and hence minus U also belongs to W1 because W1 is a subspace, and this further implies that V belongs to W1. So I have started with V belongs to W2. Now I have proved that V belongs to W1. So this further implies that W2 is contained in W1, correct? So you can prove the other way around using the just changing the W1 in terms of W2. Therefore I can write it as here, let without loss of generality, let W1 is not contained in W2. So that will take care of the other part as well, counterpart as well. Okay, so this proves that W1 and W2, if they are subspaces, then W1 union W2 is a subspace if and only if one subspace is contained in the other subspace. Otherwise it is not going to be there. Otherwise I don't know whether it is going to be a subspace or not. Okay, there is no guarantee that it will be a subspace. There are some more ways to construct subspaces using the some of the operations. Now what and all we have done so far is if two given subspaces W1 and W2 are present, then union I know how to generate a subspace, and intersection I know how to generate a subspace, and similarly now I can look for a new thing called sum of two sets. So it's a set theoretical sum only. I can define W1 plus W2 as let's say W1 plus W2 such that the first element belongs to W1 and then second element belongs to W2. So this is a addition, set addition. You see two sets are there, W1 plus W2, and that has been defined in this manner. Now I can also define one more thing. Suppose W1 and W2 are subspaces. I define something called direct sum of W1 and W2, which is W1 direct sum W2 when it is it's equal to W1 plus W2, and W1 intersection W2 is equal to singleton 0. So if W1 and W2 are two subspaces of any vector space V, then W1 direct sum W2 has been defined as the usual addition only, usual set summation, but with the restriction that W1 intersection W2 must be a singleton 0. One can verify that this is a subspace. So W1 plus W2 is a subspace. It's a subspace containing both W1 and W2. That is very clear. Why? Because W2 has a 0, so you consider W1 plus 0, that will be W1 itself. Similarly 0 plus W2 is a W2 itself, Therefore, W1 and W2 will be there. Verifying that it's a subspace is also much more clear, because each W1 and W2 is a subspace, and therefore 0 is present anyway. And then also alpha times of u plus beta times of alpha times of u plus v, and here also alpha times of u plus v will belongs to W1 and W2. Therefore, W1 plus W2 will be a subspace. There is no issue in it. So this example generates a subspace using W1 plus W2. Correct? Okay. One more thing I can say, that W1 plus W2 is the smallest subspace which contains both W1 and W2. That can be also proved. In other words, any subspace containing W1 and W2, any subspace containing W1 and W2 will also contain W1 plus W2. So let me write it here. That's one result. You can verify it very easily. I'm not going to verify it right now. So any subspace containing W1 and W2, both of them should be there, also contains W1 plus W2. It's clear. So for the same reason, W1 direct sum W2 is also subspace. There is no question on it. I can define subspaces using one more notation as well. Suppose you see a vector V in a vector space V, then you take one subspace of V. It's a subspace of V. Now look into the set V plus V, similar to the addition direction only, addition definition only. Now this has been defined as V plus this is W, small set V plus W. That's what my intention is. So V plus W such that this small w belongs to the capital W. Then this set is also a subspace of V. That can be easily proved. This is usually written as just a small v plus W. There is a name for this kind of set, is called as a coset. So this is a definition of a coset. In fact, coset containing small v. One can prove that this is also a subspace. In fact, this is a corollary of previous one. If you say W1 plus W2 is a subspace, you can easily prove that in that regard. It's not exactly the corollary, because this is not a subspace, but you can prove in the same line. It's not so difficult. So please prove it by yourself. So any coset is a subspace of V. For I can actually generate a subspace using in general I can generate the subspace using the linear combination. Now say, what do you mean by linear combination? Let's define linear combination and then say some of the things about it, and then I can generate some subspaces for that. Suppose I have V1, V2 and so on up to Vn. This is a set of vectors which is in V. Then any linear combination of this set, let's say this set is W, any linear combination of view W is of the form alpha 1 V1 plus alpha 2 V2 plus and so on plus alpha n Vn. That's it. Which means I just actually I'm adding all the vectors by multiplying with the scalars. That's it. So I multiply with some scalars, alpha n Vn, alpha n, alpha 2, and so on up to alpha n belongs to the scalar field. So this is called as a linear combination of V1, V2, Vn. Now what I can do, I can collect all such linear combinations and I can put it in a particular set. So suppose I collect all such linear combinations, so alpha 1 V1 plus and so on plus alpha n Vn, such that alpha 1 and so on up to alpha n belongs to F, any alpha 1, alpha 2, alpha n, then this generates one set, and that set is actually called as span of W. In fact, this is nothing but set of all linear combinations, of W. So this is called as a span of W. Now one can verify that span of W is always a vector space. Span of W is always going to be a vector space. For the same reason, I can prove that span of W is always a subset of V and also a subspace of V. Suppose V V is equal to R2, and then take your W is equal to some singleton 1 comma 1, say for example this is my W, then the span of W will be equal to set of all alpha times of 1 comma 1, such that alpha belongs to R itself. And then what is this? This is alpha comma alpha, such that alpha belongs to 1 itself. And what is this? This is nothing but the x coordinate and y coordinate are same, no? So this is nothing but y equal to x line. That's it. Y equal to x line, and that is a vector space. We know this already, correct? So that's what I have mentioned here. So you see the span of W, then the span of W is always a vector space always a vector space. In fact, the span of W is completely contained in V, therefore span of W is a subspace of V. Okay. Now what else we can do? So if you consider a matrix A, then the matrices is of written in terms of rows and columns, right? So rows are there and then columns are there. Now every row can be considered as a vector. Every row can be considered as a vector. So now say for example R1 is a vector, R2 is a vector, R3 is a vector, and the one up to Rn is a vector. Now collect all this R1, R2 and so on up to Rn. Then look into the span of the rows. This has a special name called row space of A. We know that span of any vector is a subspace of where it contained in, and similarly here row space of A, which has been defined as the span of the rows of A, is contained in Rn now here, and therefore this is a subspace. So row space of A is a subspace. Similarly, one can take for the span of the columns, because the columns are also vector space. Columns are also vectors. Therefore, span of C1, C2, and so on up to Cn, which is completely contained in Rn, is also a subspace of Rn, and that has a special name called column space of A. Which means, given a matrix A, I can have two trivial subspaces, something called row space of A and then column space of A, and those are nothing but the subspaces of corresponding place. Suppose if this matrix is A m by n, then there will be m rows and n columns. Therefore this would be R1, R2, this would be Rn, this is subspace of Rn, and then columns will be subspace of Rm, right? Yeah, make sure that you have the numbers properly if I even miss it. So these are some of the examples of subspace. You can generate more subspaces. You can look for more examples on subspaces. So this is where we end right now for this today's lecture. We'll see in the next lecture basis and dimension. So we'll increase a little bit more, and then we'll discuss something called basis, and something called dimension of a vector space, and hence we'll discuss the dimension of the subspaces, and we'll see some of the theorems and properties which is associated with that. Thanks a lot. We'll see you in the next lecture. Thank you.